So, as I said, I'm a statistician, so I'll bring the statistical point of view, and in particular, the Bayesian statistical point of view to this audience that was already highlighted this morning. So the general framework is that we have data, and today data will be X, 1 through Xn. We have a model that describes this data, and the model is parameterized by a vector of parameters, theta, which is d-dimensional. And as a Bayesian, we also have a prior probability distribution on the parameters that index the model. So those are the basic ingredients, and out of those ingredients, we would like to come up with some probabilistic statement about the parameter of interest. And in particular, we might want to calibrate our model. We call it point estimation. We might want to build confidence or credible intervals of the values that the parameters can take. We want to do hypothesis testing and prediction, and we might even want to do model selection, so decide which model best fits the data. So let me focus on the model to start with. So there are two main classes of models. Statistical models that are given by a closed form expression, like, for example, the Gaussian model. So the Gaussian model is indexed by two parameters, the mean and the standard deviation. So we call the parameters that index the model theta. And in this case, we have a completely closed form expression for the model. Sometimes we cannot write analytically the model, not even up to a normalizing constant. In this case, we talk about generative models, that is, models that, despite not having a closed form expression for the likelihood, can be forward simulated, meaning that if I give you values for the parameter, you can generate some pseudo data on a computer. So in particular, the Gaussian model can also be seen as a generative model. If I give you values for the mean and the standard deviation and a source of randomness, then you can generate some pseudo data that has the desired model distribution. So in this case, there is a one-to-one correspondence between a statistical model and a generative model. Sometimes such correspondence is more hidden, but for the purpose of today's talk, we will be focusing on generative models, which is a much broader class of models. That is, models that do imply a likelihood or a closed form expression for the model itself, but we cannot actually evaluate this likelihood analytically. So this type of models are everywhere, and we will call the model M theta. Theta are the parameters, and the feature of those models is that we can forward simulate the model and generate some simulated data. So those models are available in fluid dynamics, in biosimulation, in simulation of galaxies, or evolutionary biology, ecology, neuroscience, health science, meteorology. So think of it, and in pretty much any fields, you can come up with models that have this feature that you can forward simulate. Let's now focus on the probabilistic statement that we want to make on the parameter or on the model itself, given some data. Well, if we have a closed form expression for the model, we therefore have a likelihood for the parameter of interest, and we can either do maximum likelihood estimation, so estimate the parameter theta by maximizing the likelihood, or if we are Bayesians, combine the likelihood with the prior, use Bayes' theorem that was reminded to you this morning, come up with the posterior distribution, and then base our inference on the posterior distribution, either maximizing the posterior distribution or averaging, and using the posterior mean as your parameter estimate. But you realize that as soon as the likelihood or the model is not available analytically, we of course cannot maximize it, and we cannot either form the posterior distribution. So neither maximum likelihood estimation nor Bayesian inference is available to us, at least traditionally. The research that I've been doing with my research group lately focus on inference on likelihood-free generative models. So that is models where the likelihood is not available, but have this feature that we can easily forward simulate them. And we have a bunch of applications, successful application and ongoing collaborations. And among them today, I will focus on how we use likelihood-free generative models to calibrate force fields to reproduce properties measured by either simulated data or experimental data. So this is the setting of the specific application that I will talk about today, but I would like to mostly focus on the general methodology, and then I will get back to this application. So we consider MD simulations, which explore the phase space by integrating some Newton equations of motions. And this gives rise to either dynamical or thermodynamical properties for which the likelihood is typically not available analytically, unlike for forces or energies. And when we do this type of simulations, those models have different sources of uncertainties. We can be unsure about the model itself. We have uncertainty about the parameters that calibrate at best the model. There is computational uncertainty and uncertainty in the measurements of the data. So often, all these type of uncertainties are modeled through a Gaussian distribution. So if we assume that the various sources of uncertainty are Gaussians, then we have a closed form expression for the likelihood, and we can do the traditional either maximum likelihood or Bayesian inference. But this a Gaussianity assumption is often not realistic. And so we want to move away from this assumption, but this puts us in a likelihood-free framework because the likelihood will then not be available. In general, the accuracy of the underlying MD simulation depends on the force field that is used to solve the equation of motions. And for the purpose of today's talk, we will focus on the Lennard-Jones force field that we will use for helium, and for the TPI4P force field that we will use for water. And the forward simulation we will be performed with LAMMPS and GROMACS for the simulated data, and then I will also show you results on experimental data collected using either neutron or X-ray diffraction. So this is the specific application that we will focus on today, and let me give you the final results that we get on those applications. We will come up, despite not having a closed form expression for the likelihood, with a calibration of those force field parameters that show strong correlation among the parameters that we calibrate. And not only we can estimate the parameters, but we also know the uncertainty of the estimation. And we can also do model selection, so we can also decide with the framework that I will highlight, which is the best force field formalism to describe the data that we have. So we can also do, in statistical terms, model selection, which in this setting amounts to select the best force field. So how do we obtain these inferential results despite not having a likelihood in closed form, because we move away from the Gaussianity assumption? Well, we do this by using this methodology, which is called Approximate Bayesian Computation, or ABC for short. That is a fairly recent methodology that was first brought to the mainstream literature in papers in the genetics field. So you see that the first papers are in genetics and bioinformatics and molecular ecology. So it really comes from specific domain applications. And then, of course, statisticians realized how powerful this methodology is. We studied it, and we generalized it in various different ways. So what is ABC? Well, first of all, what ABC allows you to do is avoid direct evaluation of the likelihood and still be able to calibrate the model or do model selection. And we do this by using the feature of the model, which is its ability to be forward simulated. And the basic idea is that ABC allows to identify parameter values that forward simulate data points that are close to the observed data points. And this closeness is measured by some discrepancy delta, which depends on the parameter value. And when this discrepancy measure is small, we think that the parameter values that has generated the simulated data might have very likely also have generated the observed data. So this is the intuition. Let me repeat this because this is crucial and fairly simple. So given a value of the parameter, I use the fact that the model is easy to forward simulate despite not being analytically available. So on a computer, I simulate some pseudo data, let's call it XSIM, and then I look at the simulated pseudo data. If that is close to the observed data, then the value of the parameter that has generated the simulated data very likely has also generated the observed data. And we do this over and over very many times on a computer. So this is the intuition. Yes. Yes. Exactly. Exactly. Yes, thanks. This is let's put it into a context that is familiar to you. This is exactly what we do. So we parameterize the Lennard-Jones potential. Given some values of the parameter, we do the forward simulation, then we compare the simulated data with the experimental data, and we retain the values of the parameter that have generated simulated data sufficiently close to the observed data. Thank you. Yes?
How do you decide how to update the parameters? Because
yes, so the question is how do we decide to update the parameters? I will get back to this, very important point. Thank you. So this is just to remind you about the Bayesian framework. So in Bayesian statistics, we have some observed data, and we condition on the observed data. We have a model for the observed data that is indexed by some parameter theta. We put a prior distribution on the parameter. Bayes' theorem tells us that the posterior distribution is proportional to the prior times the likelihood, and the normalizing constant is called the evidence. Okay? But not having the likelihood available in closed form, the posterior is also not available. Still, this is a cartoon of what ABC does. So nature gives us data, and we draw an epsilon ball around the observed data. So this happens on the data space. Then we have the parameter space. As Bayesians, we have a prior distribution on the parameter space, which is what we think the best values of the parameter are before looking at the data. This is our prior guess. Which can be even uniform. You can express some situation of not knowing what is the best value of the parameter. So what we do is we link the parameter space to the data space through the model. So the model, given a value of the parameter, simulates on the data space. So we do this over and over. So a sample of value on the parameter space from the prior, and then I forward simulate using this feature of the model that allows us to forward simulate some simulated data. If the simulated data is outside the epsilon ball, we throw away this value of the parameter. And we keep doing this until we find some value of the parameter that generates simulated data that is sufficiently close to the observed data. And we do this over and over in supercomputer, parallelizing this procedure, which is embarrassingly parallelizable. And we retain the values of the parameter that have generated pseudo data that are close to the observed data. Now, when I tell this story to practitioners, they tell me, well, this is what we do in our calibration of the models. That's true. This is what typically is done, but this is done manually by trial and error. what we do within ABC, we formalize this, we automatize this, and we show that by doing this, the parameter values are coming really from the posterior distribution as this epsilon ball shrinks to the observed data. So as epsilon goes to 0, those green points are really from the posterior distribution. In computers, we cannot take epsilon equal to 0, especially if the data is continuous, because then we will never have a perfect match of the simulated data with the observed data. So this is why we call this approximate Bayesian computation. And the approximation comes from the fact that epsilon is not 0. But if epsilon was 0, and if we have our data on a discrete setting, then this would be exact Bayesian inference. So this is what is known as the rejection ABC, or vanilla ABC. It's the simplest form of approximate Bayesian computation. So here's the pseudocode of the cartoon that I just showed you. So this is how it works. We first sample a value of the parameter from the prior distribution. Then we forward simulate from the model some simulated data. And this can be done despite the model not be available analytically. Then we accept the value of the parameter if the distance between simulated data and the observed data is less than some epsilon threshold. And we can show that the accepted values of theta are asymptotically as epsilon goes to 0 from the correct posterior distribution. The proof is actually 3 lines, but I'll skip it. But the intuition, I think it's very strong. Now, when the data is on a big dimensional space, big data, instead of comparing the simulated data with the observed data, we summarize both the simulated data and the observed data through some summary statistics, some features that capture the relevant information contained in the data relevant for making inference on the parameters. And when practitioners do calibrate their model by trial and error, they know precisely what are the features of the data that they want to be reproduced by the calibrated model. So they know what are those summary statistics that they want to be preserved. So we call those features S, and now the comparison between the observed and the simulated data will be mediated by this summary statistics S. Now, if this summary statistics is sufficient, that is, if it captures all the information contained in the data relevant for making inference on theta, we will not be adding an additional layer of approximation to this methodology. On the other hand, unfortunately, it's not easy to find sufficient summary statistics, sufficient in the statistical sense, so we will be typically inducing an additional layer of approximation in the procedure. But that's okay, we have to live with it. The fortunate case, we are lucky because practitioners know very well what are the features of the data that they want to be reproduced by the calibrated model. So typically, we don't use this vanilla ABC, we use advanced ABC. In particular, the results I will show you on the force field calibration use adaptive population Monte Carlo ABC. How does it work? Very roughly. Instead of sampling from the prior and then doing the forward simulation, we first sample from the prior, then we perturb the parameter values using some kernel, which is a kernel that moves the parameters around and tries to bring them towards the support of the posterior distribution. And then we do the forward simulation and the comparison. So we simulate from the prior, we perturb the parameter values, forward simulate, and then do the comparison. And if the value of theta is accepted because the distance is less than the threshold, we're happy. Otherwise, we perturb again and keep going. And we do this by slowly decreasing epsilon towards 0. So we have the simulated data, the observed data. Observed data are given to us by nature. Simulated data are given to us by the forward simulation of the model. We do this comparison either on the data itself or on some summary statistics computed on the data, and we keep doing this by slowly decreasing epsilon. Now you realize that this is embarrassingly parallelizable because we can generate a vector of parameter values and do the forward simulation in parallel. And indeed, this is what we have done with ABC Pi that runs on the Swiss National Supercomputer HPCs. So let me tell you a few words about ABC Pi. Because the forward simulation can be costly, we parallelize them. And we parallelize them within ABC Pi using either MPI or Spark, or MapReduce on Spark. So those are the ways we use to parallelize. And ABC Pi is a Python suite to run ABC. It runs on supercomputers, allows reproducibility of science, and it's fairly easy to use. It implements not only the rejection ABC, but other 7 ABC samplers that have been developed since this idea came up in the past, 5 years. And then the question is, which one of those ABC algorithms we use in practice? Well, for the specific application that I'm going to show you, we decided to use this adaptive population Monte Carlo ABC because it has the best compromise in terms of speed up and efficiency. I will not go very much into the details of the HPC because you can download ABC Pi, is freely available. And everything you need to specify in order to use ABC Pi are 3 things. 1, the forward simulation model that can be either written in Python, C++, R, and then you dynamically load in. So you have to code the forward simulation. 2, you have to tell us which distance you want to use. And 3, which summary statistics or features you want to be preserved by the inferential process. So you code these 3 things in, and then we take care of everything. We parallelize, we run ABC Pi, and return the results. Moreover, you can, within ABC Pi, also do model selection, which is something I will not talk about today, but ABC allows you to also do model selection. That is, given different force fields, you can decide which one is best to use. So not only you parameterize a given force field, but you can also choose, have the data drive the selection of the best force field. So let's now go into the specific application. If you have questions, I'm happy to take questions on the general methodology, which goes well beyond this specific application. Yes? Yes, sorry. You need to use this.
How do you know when your summarizing statistics are enough to properly describe your problem, but not too much? Because you said in the previous slide that it works. When it works, it gives you 0 error on the estimate, right? But you might overshoot this, right?
Yes,
somehow.
Good question, thank you. So within ABC Pi, we do implement this paper, which does a semi-automatic way of selecting the summary statistics. So basically, you code all the summary statistics that you might think are useful to calibrate the model, and then, using the methodology of this paper, we automatically select the relevant ones, okay? So if you put even correlated summary statistics, we will be able to tell you or we automatically decide which one to keep. The problem is if you forget to use or give us or code some relevant summary statistics, well, you realize that that is the case when you test on simulated data. So on simulated data, you know the values of the parameter, you use some summary statistics. If you recover the proper values of the parameter, given the summary statistics that you've used, then most likely you will do the same on real data. So you check first on simulated data, simulated like you simulate with some given values of the parameter, and then you see whether your summary statistics allow you to recover the simulated values, the true values of the parameter, and then you run on real data. So if you have too few summary statistics, the simulated experiment will tell you. If you have too many, don't, because we will be able to tell you which ones are the relevant in an automatic fashion. Yes, yes. There are, these days, we're working on having machine learning tools tell us which are possible relevant summary statistics. So there is a research line that uses machine learning to come up with relevant summary statistics or features. It's not that hard. For those mechanistic driven model, typically the number of parameters, remember here the dimension of the space is the dimension of the parameters, okay? It's not that many, it's not the dimension, it's not the data space, okay? Okay, so that's, what you're trying to learn is the parameters. But thank you.
We have another quick question here.
Okay, just a quick question. So in the example that you had shown before, would the model not then overfit if you have too few samples? Like if that even makes sense? Because then what we were trying to do is we were trying to figure out the parameters of the simulator which generate the samples in the real data space as similarly as possible. And if then we get the samples, we would probably overfit
right.
the samples.
So if your model is over-parameterized and you have an overfitting issue, you will have that issue regardless of whether you use ABC or any other methodology. Okay, so we're not going to solve the overfitting issue. Okay, that's a model problem.
Okay.
So we're not going to solve that. But if you give us too many summary statistics, then we will be able to select the relevant ones.
Okay.
So overfitting is a matter of the parameters. If you have too many, that's like your problem.
Yeah.
But it's your problem no matter which methodology you use to calibrate your model. Okay? We will not solve this overfitting issue. Thank you.
In a way, the Bayesian approach kind of solves the parts of the overfitting, right? Having a prior help.
Yes.
Yes.
Compared with a maximum likelihood approach, the Bayesian approach through the prior does this shrinking or takes care of overfitting in some sense. Yes, that's, yes, yes.
Very briefly, I just wanted to ask, how many parameters are you fitting? So what is the dimension of your parameter space?
Typically, for those mechanistic models, the number of parameters are not many, because mechanistic models are knowledge domain driven, typically, and if you have a good understanding of the phenomenon that you're studying, the number of parameters are at most 10, okay, because they are knowledge domain driven. But ABC can be used with many more parameters, so it's not limited by using few values, few numbers of parameters, but mechanistic models or generative models, because they are knowledge domain driven, is the knowledge domain that drives the model formulation. So in statistics, but not only statistics, there's always this trade-off between a simple model with few parameters and a model that is a good understanding of the phenomenon that we're studying. Typically, we don't use complex model because then it's hard to write down the likelihood. Here, we can use complex models because we don't need to write down the likelihood. So we have our imagination free to think about the model as complex as you want, and it's driven by your understanding of the phenomenon. But since it's us understanding the phenomenon, is usually no more than 20 parameters.
We actually have a last question.
So you say that in the limit of having an epsilon which goes to 0, you sample from the true posterior distribution,
exactly.
Right? Do you have any? Can you say any? If there are any general statements about how the variance of your parameters changes compared to the? Are there some bounds that you can say something about? For instance, in the cases where you can only go down to some finite.
Yes. So thank you. So there are colleagues, the French community that is studying how fast the asymptotics of ABC, right? So yes, to answer your question, I'm not going to give you the details, but there are papers, very recent ones, like last year, that study the asymptotics of ABC. Yes, thank you. And the error bounds and everything. Yes. Okay, good. Let me go back to the example, but it's important that you understand the general methodology and how powerful it is. before looking at this specific example. Actually, two examples. So the first example is related to calibration of the first field of helium. This is the usual Lennard-Jones potential. And we take two parameters, the epsilon and the sigma, the depth of the potential well, and the finite distance at which the interparticle potential is 0. So theta, in the previous slides, now become these two parameters. The model is generative, and it can be forward simulated using online available code or routines. And the summary statistics that we use is the average ensemble over all atoms in the system at a specific time point of, e to the enthalpy contribution of a helium atom at time t, divided by the usual Boltzmann constant and the temperature of the system. Okay, so this is the summary statistics that we use. It's our choice. It works well. And then the other ingredient that I need to give you is the discrepancy measure. Well, here we use the Kullback-Leibler divergence between the probability density function of these summary statistics. Okay, so remember, you need to specify a summary statistics, a distance measure, the prior distribution. So the prior distribution here I taken to be uniform over this lower and upper bound for both the parameters. So uniform prior means that you have no idea within those bounds of what is the best value of the parameter. So it's sort of agnostic of the best value. And then you need to also to specify a perturbation kernel, because we don't use the vanilla ABC, we use this population adaptive MCM Monte Carlo ABC. And here we use a truncated, because the parameters are positive, two-dimensional Gaussian with a covariance, which is centered at the current value of theta and has a covariance that is learned from the previous particles, from the previous values of theta that have been accepted. But those are technicalities. Let me show you the results. First of all, we can calibrate the Lennard-Jones force field without assuming Gaussianity, and we calibrate it on the quantities that typically are not used for calibration, but are the quantities that you really care about. This is our benchmark, which is a paper that also uses ABC to calibrate the Lennard-Jones potential in 2016. So this is on simulated data. So here we know the true value of the parameter. This is the posterior contour plot. So they do a fairly good job, but not as good as what we do. Here you have the true and the estimated value of the distribute theta 0 and theta hat with our methodology. So we do a much better job. Besides looking at pictures, we also want to have some measures. So here is the distance between the true and the estimated value of the parameter, between what we do and what they do in that benchmark paper. And this is the final epsilon. Remember, we have this epsilon going to 0. Here we change the notation to delta, but given a certain computing time, we get much closer to the true value. Our final epsilon is much smaller. And then we move to water, and we use this potential energy, which is a Lennard-Jones plus an electrostatic interaction. Again, we have two parameters, the sigma and the epsilon, as before. And we use T4P to do the forward simulation in the ABC procedure. And we have no Gaussianity assumption again, and from experimental studies, it's typically not possible to track the time-dependent position of the water molecules, but we can learn their properties, for example, the different radial distribution functions. And in particular, here we use the radial distribution function and self-diffusion coefficient as our data, and the data is either collected through neutron or X-ray diffraction. So let me now give you the summary statistics and the distance measure, which are the two things that you need to specify. Here we have a vector of 9 different summary statistics that are obtained by first computing the distribution function of the radial between OH and OO atoms, and then computing the mean square displacement from the coordinates of the dynamical system. So basically, we first draw this distribution functions, and the summary statistics are those S1, S2, S3, S4, and so on that you see here in the images. And here is the MSD displacement, and the last summary statistics is the slope of this line. Here are the summary statistics in words. How much time do I have left?
Well, 2 or 3 minutes.
20 minutes, perfect. So, okay, so I will not tell you in words what those summary statistics are. I think the pictures are sort of self-explaining, but basically there are some features of this distribution function of radials that we want to be preserved, that we use to calibrate our ABC procedure. Okay, here they are detailed in numbers. And the distance is just the average absolute distance between the feature observed in the forward simulated data and the feature observed in the observed, computed on the observed data. Again, we have uniform priors. We use the same perturbation kernel as before. You don't need to think about the perturbation kernel. It's basically taken care by the ABC Pi procedure. GROMAX is used to do the forward simulation. And here is the results on simulated data. So here you have the true value of the parameter and the posterior contour plot. You see that there's very high correlation between the two, the sigma and the epsilon parameters that we see. And then here is the posterior prediction. So here the true Newton diffraction is the dashed line. And then we have the average prediction, which is the continuous line, and we have some confidence bounds, because remember we're Bayesian, so we can come up with error of our estimates. And here are some measure of how well we are doing using properties that are not being used to calibrate. So other summary statistics of the data, other features of the data that have not been used, they are not the S1, S9 that we use to calibrate. In particular, the heat capacity, the density, the isothermal compressibility, and dielectric constant. So those are other features, and those are the values that have been computed on the experimental data. Those are the values from the forward simulation, and those are the values that we obtain from our ABC procedure, either using Newton diffraction or X-ray, diffusion data. And most of the time we do better, even on quantities that have not been explicitly used to calibrate the model. So to conclude, I hope you see the potential of this methodology, ABC Pi, because it allows you to do sound statistical inference, to calibrate your model, to do confidence interval, error bounds, model selection. I didn't tell you anything about model selection, but it's built into this framework. And it's built into ABC Pi, which can be downloaded from GitHub. It has a documentation. It has some models that are used for simulation. Even those models that I showed you are in the documentation. And you can run it either on the Swiss National Supercomputing HPCs, or you can apply to, how's it called, HPC3, right? HPC Europe 3, right? And visit Warwick in the UK, which is a country which is in the framework, where Rito, who is the guy behind ABC Pi, is, and you can learn everything about ABC Pi, spending there 3 weeks or more. And I would like also to thank Michele Parinello and Alessandro Laio for helpful discussions on this research line. Thank you.
So we had plenty of questions, but maybe while the next speaker prepares the slide, we can take another one if there is, yeah, there is one.
So what are the limitations of the model? Like, if you want to fit a larger molecular model, or if the simulation to obtain the summary statistics is really time-consuming? Can you comment on that?
Well, so if things are time-consuming, especially the limitation is in the forward simulation or in computing the summary statistics, of course, the methodology is slow. But in some sense, this is the only thing that you can do if you don't have a closed form expression for the likelihood. So, and it's sound statistically, from a statistical point of view. So you run everything in parallel, and you take the time that you have to submit your, paper or your thesis, and you live with that. There's not much more than you can do if the model is not available in closed form, or if you want to use a sufficient flexible and realistic model that does not have a closed form expression for the likelihood. So basically, ABC frees your imagination from having to write down an expression for the likelihood. All other methodologies that have been discussed need to evaluate this likelihood. If you don't have it and you want to do statistical inference rather than machine learning, then this is the methodology that I would recommend. And yes, if things are slow, well, that's it. But having everything parallelized and run on supercomputers gets around this, slow
So
issue.
actually, there's plenty of other questions for what I understood, but we don't have time, so I recommend people go and talk directly to Antonietta.
Yes, I'll be around.
Later in the coffee break. Let's thank her again. And